Last video in section 2.6. So in this video, we're going to do some changing variables in order to evaluate trig limits by the squeeze theorem. Or rather, we're going to use the limits that we already have computed by the squeeze theorem in these cases. So what we're going to have, our first example, we'll do two examples. Limit as h goes to 0 of sine of 6h over h. And so this looks very reminiscent of sine of theta over theta as a limit as theta goes to 0. Now realize that one way that we could approach this is that we could try to work through everything, do the same things that we've done before, come up with appropriate bounding functions on sine of 6h over h, this and this, for example. But there would be some argument there that you'd have to do to argue that those are the right bounds that you need to use. And as it turns out, those wouldn't be the right bounds to use. You'd have to do something else, and that could get tricky. So instead, what we're going to do is that we're going to approach this by changing variables, as it says here. We're going to do a substitution. And so we're very comfortable with having sine theta. We have sine of 6h, so that suggests that we're going to set theta equal to 6h. And so if we do that, well, theta is 6h, then h is going to be theta over 6, so that can replace our denominator. And so the expression we're taking the limit of is sine of theta over 6. Now we have to think about, okay, it's a limit of what? Well, we could say it's the limit as h goes to 0, and that will be true, but we don't have any h's over there. And so we want something in terms of theta. And so realize theta is just a multiple of 6. As h is going to 0, as h is getting really, 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 really close to 0, theta is also getting really, really close to 0 as well. So h going to 0 is the same thing as theta going to 0. So here we have limit as theta goes to 0, sine of theta over 6. Now this, in the denominator, we can move that upstairs, or in fact, it's a constant multiple, we can move it all the way outside, and so we're going to end up with 6 times the limit as theta goes to 0 of sine theta over theta. Hey, I think we know how to do that limit, 6 times 1, and so our answer here is 6. So we use the fact that we already knew from the squeeze theorem, and we here produce that without too much work, we get sine of 6h over h. So this is nice. We don't have to rederive everything from scratch. We can just use our previously derived fact. So one last example that's in the same vein, but maybe ever so slightly more going on, is what happens if I ask about the limit as x goes to 0 of tangent of 5x over tangent of 3x. Well, everything that we've done before is in terms of sines and cosines. We have tangents, so that suggests that we should rewrite this in terms of sines and cosines. So tangent is sine of 5x over cosine of 5x. Tangent of 3x is sine of 3x over cosine of 3x. And let's rearrange this just a bit to end up with, to put the sines in one place. And then the cosines in one place. Know that this cosine of 5x is in the denominator. And this cosine of 3x comes all the way upstairs to be in the numerator. And so this is what we have, and this is starting to look attractive. Well, at this point, we want to rewrite things. So what do we have right now? We know that we're looking for things of the form where we have like a sine of theta over theta type of thing going on. So really, what we want this, and we have to think about what we want here, sine of 5x, what's the thing that we want to have in our denominator? So the best thing that we could have in our denominator is 5x. Because then we could do a change of, it was just looking at this by itself, obviously there's more to come here, but we're just looking at this by itself, a change of variables. Theta is equal to 5x would give us sine theta over theta. We know what that limit is. Similarly, so we have a sine of 3x. Well, what do we want upstairs? A 3x would be great, because once again, we can do a change of variables and have theta over sine theta, and we could take care of that. So then we have cosine of 3x over cosine of 5x. That still is chilling over there. And let's see, the only change that we made was that we multiplied the numerator by 5/3. We put a 3x. We have a 3x in the numerator, we have a 5x in the denominator. So the only net change is that we have to multiply all of this by 5/3. And so by the product law, we can break this up as the limit as x goes to 0 of sine of 5x over 5x times the limit as x goes to 0 of 3x over sine of 3x times the limit as x goes to 0 of cosine of 3x over cosine of 5x. We have a factor of 5/3 floating around. We could just move that. That's a constant. Let's just move that out in front. So here we're applying the product law because each one of these three limits will exist, and we'll see that, and we'll end up evaluating that on the next page. So right now, what do we have? So we know we need to have limit as x goes to 0 of sine of 5x over 5x, a change of variable, that theta is 5x, makes us a limit as theta goes to 0, sine theta over theta. Guess what? That's 1. We also have the limit as x goes to 0 of 3x over sine of 3x. So a change of variables, theta is 3x, makes this, the limit as theta goes to 0 of theta over sine theta. And so now you might say, oh, this is something different than what we have before, but this is just the limit as theta goes to 0 of sine theta over theta to the minus 1 power. And so by our power law, this is just the whole limit, because if the limit exists and it's not 0, and that's the case here, this is just the whole thing raised to the minus 1 power. So it's 1 to raise to the minus 1 power, which is just 1. So coming back to this slide, what do we have? 5/3 times this limit was 1, this limit was 1, and then finally, it's pretty easy to realize as x goes to 0, cosine 3x and cosine 5x, those are both just going to 1. So 5/3 times 1 times 1, and so our final answer is 5/3. So that is one final example of how we can do several different changes of variables and using the previously derived sine theta or theta limit, which is extremely important in order to evaluate these trigonometric limits. And with that, we are all done with section 2.6.